Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this short but rewarding section, we meet one of the most important constants in all of mathematics, the number e. Everything we need is already in our hands. We have a solid theory of series, we know the geometric series, and we have upper and lower limits. We will put those tools to work. We will define E as the sum of a rapidly converging series, then prove that the very same number arises from a completely different limit, the limit of 1 plus 1 over n, raised to the power n. Finally, we will use a sharp estimate on how fast the series converges to prove something striking. The number E is irrational. Let's begin. Here is our plan. We start with motivation, why E deserves its own section and what makes it special. Then we give the official definition of E as an infinite series and check that the series actually converges. Next comes the first big theorem, which shows that E is also the limit of 1 plus 1 over n to the n. After that, we measure how quickly the defining series converges, obtaining a clean error estimate. That estimate is the key to the final result, the proof that E is irrational. We close with a summary of what we have learned. Let's set the stage. The number E is one of the fundamental constants of mathematics, sitting alongside the number pi in importance. It is the natural base for exponentials and logarithms. It governs compound growth and decay, and it appears throughout analysis, probability, and number theory. Its numerical value is roughly 2.718, but a number this important deserves a precise definition, not just a decimal approximation. Next, let's see what tools we will use to pin it down. Here is the good news. We do not need any new machinery. Over the last several sections, we built a careful theory of infinite series. We analyzed the geometric series in detail, and we introduced upper and lower limits. Those are exactly the tools needed to define E rigorously and to study it. This section is really a showcase. It demonstrates how the abstract theory pays off on a concrete and famous example. Next, let's preview the two surprises waiting for us. This section holds two surprises. The first is that E, which we will define as an infinite series, turns out to equal a completely different looking limit, the limit of 1 plus 1 over n, all raised to the power n. The fact that these two processes land on the same number is not obvious, and the proof is a beautiful exercise in handling limits. The second surprise is that E is irrational. It cannot be written as a ratio of two integers. We will prove both of these. Let's start by writing down the definition. Here is the official definition. The number E is defined to be the sum of the infinite series whose terms are 1 over n, factorial, summed from n equals 0 to infinity. So the terms are 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, and so on. We need a convention for the factorial. For n at least 1, n factorial is the product 1 times 2 times 3, up to n, and by convention, 0 factorial is defined to be 1. With that convention, the first two terms of the series are both equal to 1. But before we can call this a definition, we must check that the series actually converges. Let's do that next. To check convergence, we look at the partial sums. The partial sum S sub E n is what you get by adding up the first several terms of the series. 1 plus 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3, and so on, up to 1 over the product of all the integers from 1 to n. Because every term is positive, the partial sums keep increasing as we include more of them. And we proved earlier that a series of non-negative terms converges exactly when its partial sums stay bounded above. So the whole question of convergence reduces to a single thing. Can we find a ceiling that the partial sums never rise past? Next, let's compare term by term with a geometric series. Now the key comparison. Each factorial k factorial is a product of k numbers, and from the second factor onward, every factor is at least 2. So k factorial is at least 2 to the power k minus 1. Turning that around, 1 over k factorial is at most 1 over 2 to the k minus 1. Replacing every term of s sub n by the corresponding power of 1/2 gives a strictly larger sum, shown on the slide. We have bounded our partial sum above by a partial sum of the geometric series with ratio 1/2. Next, let's add up that geometric piece. The geometric part, 1 plus 1/2 plus 1/4, and so on, is a partial sum of a geometric series with ratio 1/2, and that whole geometric series sums to 2. So the bracketed piece is less than 2. Adding the leading one, every partial sum s sub n is less than 3. The partial sums are increasing and bounded above by 3, so the series converges. The definition of E makes sense, and we already know E lies somewhere between 2 and 3. Next, let's picture this convergence on a number line. This picture shows the partial sums marching toward E on the number line. The blue dots are the partial sums s sub 0, s sub 1, s sub 2, s sub 3, and so on. The first jump from s sub 0 to s sub 1 is large, but after that the dots crowd together very quickly and pile up just below the dark red mark labeled E. The dashed orange line on the right at the value 3 is the upper bound we just proved. Because the sequence is increasing and never crosses 3, it converges, and its limit sits between 2 and 3. Notice how rapidly the dots converge. That rapid convergence is worth a closer look. Before moving on, one observation worth keeping in mind. The series for E converges very rapidly, even faster than a geometric series, because the factorial in the denominator grows faster than any fixed power. Practically, this means that adding just a handful of terms already gives E to many decimal places. We will make the word rapidly completely precise a little later when we derive a sharp bound on the error. For now, let's turn to the first major theorem, which reveals E hiding inside a very different limit. Here is the first theorem. It says that the limit, as n goes to infinity, of 1 plus 1 over n, all raised to the power n, is exactly the number E we just defined. The number line lets you watch it happen. The blue dots are the values t sub 1, t sub 2, t sub 3, t sub 5, and t sub 10, and they climb steadily from left to right toward the dark red mark at E. Notice how slowly they climb. Even t sub 10 has only reached about 2.59, while E is about 2.72. So this limit creeps toward E, unlike the series which raced ahead. Still, the theorem is remarkable. A sum of reciprocal factorials and a shrinking base raised to a growing power land on the very same number. The proof is a fine illustration of working with limits. Let's lay out the strategy. Before the formal proof, here is the plan. We name the sequence. T sub n is 1 plus 1 over n to the n. The strategy is a squeeze, but a squeeze on the upper and lower limits rather than on the sequence directly. First, we expand epsilon sub n using the binomial theorem. Second, we compare it term by term with the partial sum s sub n of the series for E. This gives t sub n at most s sub n, which pushes the upper limit of t sub n below E. Third, we bound t sub n from below by keeping only finitely many terms. This pushes the lower limit of t sub n above E. Finally, since the upper limit is at most E, and the lower limit is at least E, the sequence must converge to E. Let's begin. We begin by giving names to the two players. The sequence S sub n is the partial sum of the series for E, the sum of 1 over k, factorial for k, from 0 to n. We have already shown this converges to E. The sequence t sub n is the 1 in the theorem, 1 plus 1 over n, raised to the power n. Our goal is to show that t sub n also converges to E. The link between them will come from expanding t sub n. Next, let's apply the binomial theorem. Step 2. Expand t sub n using the binomial theorem. The first line on the slide is the raw expansion. A typical term, there is a binomial coefficient, that product of descending integers divided by k factorial multiplied by 1 over n, raised to the power k. The second and third lines tidy each term up. The trick is to spread the powers of n in the denominator across the descending factors in the numerator. The product n times n minus 1, and so on, divided by n to the k, turns into 1 times 1 minus 1 over n times 1 minus 2 over n, and so forth. So every term collapses to 1 over k, factorial multiplied by a string of factors of the form 1 minus j over n. Now look at the shape of the result. Term by term, it mirrors the partial sum s sub n, the very same 1 over k factorial appearing, except each term is now dampened by those factors 1 minus j over n, every one of which is positive, and at most 1. So each term of t sub n is a shrunken copy of the matching term of s sub n. Let's exploit that comparison next. Step 3. Because each damping factor is at most 1, discarding all of them only increases the value. Term by term, t sub n is less than or equal to et sub n for every. Now we take upper limits on both sides. By theorem 3.19, if one sequence stays below another, then its upper limit stays below the limit of the other. The sequence s sub n converges to E, so the upper limit of t sub n is at most E. Call this equation 14. That is 1/2 of the squeeze. Next, we need a lower bound, and that takes a slightly cleverer move. Step 4. For the lower bound, we use a different idea. The expansion of t sub n has lots of terms, and every single one of them is positive. So if we throw away all the terms past a fixed cutoff m, the sum can only get smaller. That gives the inequality on the slide. For n, at least m, t sub n is at least the truncated sum that keeps only the first m plus 1 terms. The point of freezing anium is that the truncated sum has a fixed, finite number of terms, no matter how large n gets. That is what makes the next step possible. Let's take the limit in n. Step 5. Now hold m fixed and let n go to infinity in the truncated lower bound. The truncated sum has only finitely many terms, and in each one, the damping factors 1 minus j over n all tend to 1 as n grows. So the whole truncated sum tends to 1 plus 1 plus 1 over 2 factorial, up to 1 over m factorial, which is exactly the partial sum s sub m. Since t sub n stays above the truncated sum, its lower limit stays above the limiting value. We conclude that S sub m is less than or equal to the lower limit of t sub n, and this holds for every fixed m. One more limit to take. Step 6. We have just shown that every partial sum S sub m lies below the lower limit of t sub n. The right-hand side is one fixed number. It does not depend on m, so we may let m go to infinity. The partial sums S sub m converge to E, and a limit of quantities all sitting below a fixed bound cannot exceed that bound. This is the principle recalled in the gray box, a consequence of Theorem 3.19. Therefore, E is less than or equal to the lower limit of t sub n. Call this equation 15. We now have both halves of the squeeze. Let's put them together. Now we combine equations 14 and 15. The diagram shows the squeeze. The green arrow on top says the upper limit of t sub un sits at or below E. The blue arrow underneath says E sits at or below the lower limit of t sub n. Now read the chain of inequalities on the slide. We start at E. By equation 15, E is at most the lower limit. For any sequence, the lower limit is always at most the upper limit, and that holds automatically. And by equation 14, the upper limit is at most E. So the chain begins at E and ends at E, with the lower and upper limits trapped in between. Everything in the chain is therefore pinned to the single value E. And when the lower and upper limits of a sequence agree, the sequence itself converges to that common value. Therefore, t sub n converges to E, and the theorem is proved. Next, let's measure exactly how fast the original series converges. We promised to make the word rapidly precise. The error in using the partial sum S sub n as an approximation to E is exactly the tail of the series, the sum of all the terms we left out. That tail is 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus 1 over n plus 3 factorial, and so on. Since every term is positive, the error is certainly positive. S sub n underestimates E. The question is how large the tail can be. Let's bound it. Here's the trick. Factor 1 over n plus 1 factorial out of every term of the tail. The next term then carries a factor 1 over n plus 2 factorial divided by n plus 1 factorial, which is 1 over n plus 2. We overestimate that by 1 over n plus 1. The term after that gets overestimated by 1 over n plus 1 squared, and so on. So the tail is less than 1 over n plus 1 factorial times a geometric series with ratio 1 over n plus 1. That geometric series sums neatly, and after simplification, the whole bound collapses to 1 over n factorial times n. This is equation 16. The error is positive and strictly less than 1 over n factorial times n. Let's see what that means in practice. Let's put a number on it. Take n equal to 10. Then the error E minus s sub 10 is less than 1 over 10 factorial times 10. 10 factorial is about 3.6 million. So the denominator exceeds 36 million, and the error is smaller than 10 to the minus 7. In words, adding just 11 terms of the series, the terms up through 1 over 10 factorial already determines E to better than 7 decimal places. That is what rapid convergence means here. But estimate 16 is not only useful for computation, it also has real theoretical power, and in the next section we use it to prove that E is irrational. Now the second surprise. Theorem 332 states that E is irrational. That means E cannot be written as a fraction p over q with p and q integers. Its decimal expansion never settles into a repeating pattern. The proof is short and elegant. It is a proof by contradiction. We assume E is rational and derive an impossibility. The engine driving the contradiction is the error estimate 16 we just proved. Let's outline the argument. Here is the high-level strategy. We want to rule out writing E as p over q with p and q positive integers. We assume, for contradiction, that such a representation exists. Then we take the error estimate 16 and multiply it through by q factorial. This traps the quantity q factorial times the difference e minus e's sub q, strictly between 0 and 1. Next we show, using the assumption, that this same quantity is in fact a whole number, an integer, but there is no integer strictly between 0 and 1. That contradiction kills the assumption. Let's carry it out. Step 1. Assume E equals p over q with p and q positive integers. Estimate 16, applied with n equal to q, says that E minus s sub q lies strictly between 0 and 1 over q, factorial times q. Multiply that whole inequality by q factorial. The result, equation 17, says that q factorial times the difference E minus s sub q lies strictly between 0 and 1 over q. Since q is at least 1, 1 over q is at most 1. So this quantity is trapped strictly between 0 and 1. Remember that fact. Next, we show the very same quantity is an integer. Step 2. Look at q factorial times e. Under our assumption, e is p over q, so q factorial times e is q factorial times p divided by q. But q factorial contains the factor q. So the q in the denominator cancels, leaving q minus 1 factorial times p. That is a product of integers, hence an integer. So q factorial times e is a whole number. This is the only place where the rationality assumption is used. Next, we handle the other piece. Step 3. Now consider q factorial times the partial sum s sub q. The partial sum is 1 plus 1 plus 1 over 2 factorial up to 1 over q factorial. Multiply each term by q factorial. A typical term becomes q factorial divided by k factorial, with k running from 0 up to q. Since k is at most q, that quotient is a product of consecutive integers, so every term is an integer. A sum of integers is an integer. Therefore, q factorial times s sub q is a whole number too. No assumption was needed here. This part is just arithmetic. Let's collect the pieces. Step 4 ties it all together. From steps 2 and 3, both q factorial times e and q factorial times s sub q are integers. Their difference is q factorial times the quantity e minus c sub q, so that difference is an integer as well. But equation 17 told us this very quantity lies strictly between 0 and 1. The picture makes the clash vivid. The red segment is the stretch between the integers 0 and 1, and the hollow circles at its two ends mark that 0 and 1 themselves are excluded. There is simply no integer sitting inside that stretch. We have produced an integer strictly between 0 and 1, which is impossible. The assumption that E is rational must be false. Therefore, E is irrational, and the proof is complete. One final remark. The result we proved can be pushed much further. Not only is E irrational, it is transcendental. A transcendental number is one that is not a root of any polynomial with integer coefficients. Irrationality only rules out the simplest case, where E satisfies a degree 1 equation, namely q times E minus p equals 0. Transcendence rules out polynomial equations of every degree. That is a far stronger and much harder statement. Rudin does not prove it here, but points to simple proofs in the books by Niven and by Herstein. With that, let's summarize the section. Let's review what we accomplished. We began with definition 330. The number e is the sum of the series of reciprocal factorials. By comparing term by term with a geometric series, we showed the partial sums stay below 3. So the series converges and e lies between 2 and 3. Next, let's recall the limit formula. The first major theorem, Theorem 331, revealed a second face of e. It is also the limit of 1 plus 1 over n raised to the n. The proof was a squeeze argument. Expanding with the binomial theorem gave an upper bound that pushed the upper limit below. Truncating to finitely many terms gave a lower bound that pushed the lower limit above e. The two together pinned the limit exactly at e. Next, the convergence rate. We then measured how fast the defining series converges. The tail estimate, equation 16, says the error e minus s sub n is less than 1 over n factorial times n. With just 11 terms, this gives e accurate to 7 decimal places. That same estimate did double duty. Let's recall its theoretical payoff. Finally, estimate 16 powered the proof of theorem 3.32. Assuming a were a fraction p over q, multiplying the estimate by q factorial trapped an integer strictly between 0 and 1, an impossibility. So e is irrational, and in fact, as we noted, it is transcendental. In the next section, we leave e behind and develop general convergence tests, the root test and the ratio test, which let us decide whether a wide range of series converge without needing a clever comparison each time. Thanks for watching, and see you in the next section.